Okay, welcome everybody to the session on fluid control and synthesis. My name is Chris Woitan from IST Austria. We have 4 exciting talks today. The first talk is going to be an efficient solver for space-time control of smoke. The authors are Zhirong Pan and Dinesh Minocha.
Okay, so I'm going to talk about our recent work at UNC on a new solver for space-time optimal control of smoke. So in general, we want to solve an instance of a directable smoke animation problem. This is a long-standing problem with a lot of applications in special effects and movie industry. Over the years, many algorithms have been developed, bringing a variety of user interface, such as keyframe-based interface, sketch interface, and data-driven interface. But we built ourselves on the keyframe-based interface in this work. The other interfaces are very useful for different applications, but most of them are not physically based. So more specifically, our method takes as input a temporally sparse set of keyframes, and the output is then smoke animation, where the smoke shape looks like these keyframes at a set of given time instances, like this video. So before we go into the details of our method, we want to review 2 complementary previous methods to solve this problem. One of them is the PD controller, which is computationally very efficient, but they require more user input. The other one is the optimal controller, which is more user-friendly, but they are costly to compute. So the principle of PD controller is very simple. We just compare the current keyframe and the current smoke shape, and we then make our control force proportional to the shape difference. So from this, you can easily understand that there are many, although there are many varieties of PD controller, but almost all of them look at only the current time step. So they're very efficient. They only add marginal overhead to an existing smoke simulator. But in this way, you need 1 keyframe for every time step, and the results are generally sensitive to several parameters, such as control force coefficients and damping coefficients, which is used for mostly for stabilization. So the other kind of method is the optimal controller. The big difference here is that they only require a temporary sparse set of keyframes. Let's say we are given 2 distance keyframes, A and B, and the methods then need to figure out what is the control force and the configuration of smoke and then intermediary time step. So the optimal controller solves this problem using a space-time optimization. Given a set of keyframes, it searches for the optimally controlled smoke animation that match these keyframes the best, using control forces with smallest possible magnitude. And also, the dynamics equations need to be satisfied at every time step. In our case, this means that the smoke shape is driven by the velocity, and the velocity in turn is driven by the Navier-Stokes, which is controlled by a control force F here. And the output of this optimization is the trajectory of the control force and the smoke state variables. The conventional method solves this optimization using gradient-based method. So let's say we start from a tentative solution represented using the control force trajectory. We first need to run a full path of fluid simulation to recover the smoke shapes. And then we can determine how well these smoke shapes match the keyframes, and also determine in which direction we should update this keyframe so that we can reduce the objective function. Of course, the bottleneck in this procedure is the repeated fluid simulation in each gradient computation. So in summary, although the optimal controller is very user-friendly by requiring least keyframes, and they are very robust to parameters, they are computationally close to impractical. This is, of course, due to the high-dimensional search space and the large number of PDE constraints, or the Navier-Stokes constraints. Both of these are proportional to the number of grid styles and the number of time steps. In our experiments using moderate resolution and a small number of time steps, the search space dimension can be as high as 10 to the order of 6 in 2D and 8 in 3D. And the typical optimization takes more than 2 days on desktop machine using the gradient-based method. So in this work, we used exactly the same original formulation of optimal control, but proposed a new solver. That solver exploits the special structure of the problem to achieve faster computation with guaranteed performance. So our idea is actually very simple. We noticed that the bottleneck of original solver is repeated Navier-Stokes solve in each iteration. So what we want to do is to replace this with an approximate version of Navier-Stokes solve. But in addition, we want to keep track of this approximation across iterations so that they approximate the exact solution on convergence. In this way, our method can converge to the solution with same quality as conventional method, but greatly save computation. This means that all the constraints are satisfied arbitrarily well. So to realize this idea, we developed a space-time version of multigrid solver. The multigrid solver is well known in the community to usually solve boson equation to ensure that your smoke is incompressible. And here we extend this idea to a system of nonlinear equations, and we want to solve the smoke state variables for all time steps at once. The point here is that the multigrid solver is iterative scheme by and in itself, so that we do not need to start from scratch. We can warm start it from last solutions, and this is how we achieve approximate Navier-Stokes approximation. So the idea of multigrid is very simple to understand. Let's say we have a system of equations discretized from a uniform grid, and instead of solving this system all at once, we can solve equation related to one grid cell separately and all at once. But the solution is, for each cell is spread to neighboring cells with the help of a grid cell hierarchy. The solutions of these cells are interpolated back and forth among this hierarchy to accelerate information spreading. So to develop this a space-time extension to this conventional multigrid method, we need to start from this original problem formulation. We notice that this is a joint optimization in the smoke shape, the control force, and velocity. But if we are optimizing only with respect to the control force and velocity, we fix the smoke shape, then the whole optimization is not related with the advection equation. So we call this the NS subproblem. Then, if we fix the control force and only update the smoke shape and velocity, then the Navier-Stokes, the true dynamics equation is not related. We call this advection subproblem. Of course, the bottleneck is in the first subproblem where all the dynamics happens there. For this problem, we need further development. So its structure lies in its first order optimality condition. If we use Lagrange multiplier for the NS constraints, and we require that the gradient of the whole problem vanish, we get a system of nonlinear equations which can then be rearranged into this block tridiagonal form. This is a system equation that any locally optimal velocity, control force, and multiplier must be satisfied. So we can use this tridiagonal form as a building block for a space-time version of multigrid. This is done by replacing the conventional linear equation with our block tridiagonal system of equation for each cell, and we solve the subset of equations for each cell in parallel. And we also need to replace the spatial hierarchy with a space-time hierarchy. But we want to emphasize that we only perform coarsening along the spatial axis, so that in each hierarchy we have the same number of time steps. This avoids insufficient resolution along the temporal axis and greatly boosts the performance of multigrid convergence. This is actually a cheap modification to the conventional multigrid because for each grid cell, we only have a very small tridiagonal system. Here, the block size is constant for each cell. It's 14 in 3D cases, and the number of blocks is proportional to the number of time steps. But since this is a tridiagonal system, we have very fast linear time solution, and they can be solved in parallel. So now we have accomplished our introduction of the main solver, the NS subproblem solver. The remaining problem is to solve the other advection problem. This is much easier. There are no actual dynamics happens in this problem. But we still use a little bit trick here. We want to introduce a new realization of advection operator. Our operator should be unconditionally stable, and it's easily differentiable so that we can do optimization using very large time step size to save the number of variables we want to search for. This is why we use this upwinding exponential integrator. being an upwinding integrator means that we use fixed stencil. We don't do any cell search as compared with conventional semi-Lagrangian or MAC-COMAC, this kind of method. So it avoids discontinuity across cell boundaries. And as you can see on the right, using our method, we can avoid a lot of local minima and leads to smoother keyframe match on the very large time step size of 0.2 seconds. So now we can summarize one outer loop of our method. It consists of a solve of the NS subproblem using the spacetime multigrid, which is warm started from last iteration. We don't start from scratch. And the one solve of the advection subproblem using conventional gradient-based method, but with exponential advection operator. A minor problem with this solver pipeline is that a multigrid solver, especially the nonlinear version, is not guaranteed to converge. But we can, if we use very simple modification, this convergence guarantee can be provided. This is done by introducing diagonal regularization to this tree-diagonal system. We can show that using large enough regularization, the solver reduced to a conventional gradient-based method, but in practice, a little bit regularization provide convergence guarantee. And for the other subproblem, we use simple line search that guarantee function value decrease. So this is the main structure of our solver, and you can refer to our paper for more details on the convergence proof and the building of multigrid. So now we show some of the results. One of the main benefits of optimal controller is that we can easily balance the number of smoke-like behaviors or details and the keyframe matching exactness by tuning the only parameter exposed to user, which is the weighting of regularization, force regularization. But as we increase the regularization by 100 times, the computational time also increased from 1 to 3 hours. And another important comparison is with PD controller. Here we pick a typical implementation, which is also widely used. This method has 3 parameters, but we can always fine-tune these parameters so that the results look very similar to an optimal controller. A PD controller's results are generally considered to be very sensitive to the parameters. If we change the parameter a little bit, we can easily get inexact match or a lot of escaped smoke around the keyframes. But this is compensated by the fact that PD controller is very efficient to compute. You can do a lot of design loops to get good results. So our method is also stable on the longer sequence and more keyframes. Here we have 3 keyframes. You can see a lot of smoke-like behavior in between. And the computational time is less than 2 hours on a desktop machine. But in 3D cases, the computational time is still more than 10 hours. Again, for larger regularization, the computational time increased a little bit here. This is our longest example with 2 keyframes, 120 time steps, but the computational time actually decreased. So from this, we can see that the complexity of keyframe and the number of keyframes is more important factor influencing the computational time. We could profile the performance of our method as compared with conventional gradient-based method in 2 ways. First, we compare the performance in solving only the NS subproblem. You can see that under 2 different resolutions, our spacetime multigrid has almost same convergence history. This is a remarkable feature of resolution-independent convergence for multigrid as compared with the gradient-based method on the right. But our method not only saves the number of iterations, but each iteration is also cheaper. We are only doing 1 pass of refinement to Navier-Stokes approximation in each iteration as compared with the whole NS solve. Then we compare the performance in solving the whole problem, not just one subproblem. And for 2D examples, our method achieves 8 to 10 times faster convergence as compared with the LBFGS method, which is a typical gradient-based implementation. But for 3D cases, we cut the gradient computation after 2 days if it does not converge, so that we cannot get an effective comparison. But a minor drawback of our method is that it requires twice as much memory because we need to store not just the primal variables, the smoke state, the control force, but also the Lagrangian multipliers for each variable, so twice as much memory. In our moderate resolution experiments, the biggest memory cost is 6 gigabytes, which is still manageable. So now we can conclude. In this work, we propose a new optimal controller solver that uses approximate Navier solution instead of exact solve again. And the main idea is to single out Navier-Stokes problem and develop a space-time multigrid to iteratively refine the solution there. This achieves much better convergence behavior with guaranteed convergence. But the current implementation still have some limitations. I think there are 3 of them. The obvious limitation is that we are currently limited to uniform grid and the single-phase flow, although theoretically we can extend to other discretizations such as triangle or tetrahedral mesh. Accounting for free surface is still difficult. And we do not take into account solid obstacles in the domain. This might require a new coordinating scheme. And finally, the current implementation is still more complex than a simple PD controller, which is a minor modification to an existing simulator. So in the future, we're first considering to account for the internal boundaries. This might require a new distance metric because the 2 cells that are considered close to each other may not be actually close when there are solid boundary in between them. And also, we're considering to combine the merits of PD controller and optimal controller. A PD controller always consider one time step, and the optimal controller consider all the time steps. So maybe looking ahead, a fixed number of small time steps is helpful. So, so this is all I want to cover today, and I want to thank the supporting organizations, and I can take questions. Please.
Thank you for the talk. We have time for questions, so please come up to the microphones if you have anything to ask. Okay, I will start with a question. So the idea of replacing the exact Navier-Stokes each iteration seems to, obviously it changes the objective function a bit because you have a different solution, right? And it seems like what you're doing is actually beneficial and that it's filtering the objective function and getting rid of higher frequency things that can cause local minima. And so you might actually be more likely to hit the right answer than doing it brute force. Can you talk a bit more about how the filtering, how the multigrid idea filters the actual objective function? Or can you talk a bit about local minima and things like this?
Yes, and actually our method will always converge to a very different local minima compared with the gradient-based method. But if you're talking about the quality of, measurable quality of the solution, like the constraint satisfaction and the amount of details, I believe they are all very satisfactory. So actually, there's one detail I didn't cover. In the separation of the whole problem, we need to introduce a slack variable. So this slack variable, if it's not consistent, then you might need like more iterations. So in conclusion, I think to get better detailed results, to avoid local minimas, you need more iterations.
Out of curiosity, have you actually measured the objective function value using your method versus others to see if your local minima are actually better?
Yes, we always use same stopping criteria. So, but our method always converge to an inexact, because we use iterative refinement, we always use an inexact NS convergence criterion, but that's very, very small actually. Yes.
Okay, I will ask another question if this is okay. What was my question going to be? I wanted to ask about the general field of optimal control for physics simulation, right? It's a very high-dimensional problem, yeah. Especially if you want detailed answers. And so going into space-time is 4D, and the resolution of your problem is potentially huge. And it seems like you have by far the fastest method for solving this problem, but it's still nowhere close to like real time, for example.
Yes.
You mentioned some ideas of combining PD controllers with optimal control. Do you think there's any hope for optimal control alone being fast enough to play with interactively, for example?
I think we are still far away from there.
I agree we're far from it, but do you think that it's an unattainable goal?
But let's say we have our target is a distant keyframe, and like you expect, we need to use a lot of time steps, and using optimal controller is not a sensible solution. So maybe you want to control a fixed small number of time steps. That's I think much more practical in certain cases. Yeah.
Okay, thank you very much for the talk. Okay. The next talk in the session will be Interpolations of Smoke and Liquid Simulations, and the speaker will be Neil Turai.
Yes, thank you for the introduction. Welcome, everyone. I'm Niels Thürer from the Technical University of Munich, and I will be talking about interpolating fluid simulations in the following. So let me first motivate this topic a bit. We are dealing with fluid effects here, obviously, being in a fluid session. And the typical approach we have for these simulations is we take our model equations, we discretize them, specify boundary conditions, and then we can approximate a solution. That might look like this here, a drop falling into a pool of water. What I want to look at in the following a bit more are sets of solutions. So we have a whole space of liquid behavior. For example, what you can see here, a drop of liquid falling at different positions with a different size, and then if we compute these solutions, we might actually get a pretty complex behavior. As you can see here, especially towards the end, the behavior differs quite a bit in how these splashes turn out in the end. And that is what I want to focus on in the following. So applications where we actually have these regions of behavior and we know in advance we want to work in a certain area of flow behavior. That might actually be a movie production where we have a certain effect, and then an artist might produce a sequence of simulations shown here with these silhouettes. And then, yeah, typical thing might be that the director says, yeah, this one is nice, but move a few of the drops in a different position. And we typically have to discard all of those and try to tweak the boundary conditions to get some different solution that hopefully then satisfies the client a bit more, and then we iterate on that, which is typically a cumbersome process. Or another application might be that we interactively want to work with a fluid simulation and have a user actually somehow influence the simulation. In the following, or the method I'll be talking about, actually we'll use space-time deformations to realize such applications. Yeah, let me specify a bit more what we're looking at here. So we're starting with some initial conditions for the simulation, and then we have some external parameter that will in the following be called alpha to change the simulation. So here the example shows that this drop above the basin might be moved. That could really be any external parameter. It could be viscosity or even discretization. Doesn't really matter too much. We're computing solutions with respect to that parameter. We get a surface out of it, and that will be in the following this gamma. That depends now on the parameter we choose. And of course, the parameter could have any dimension. We could move this drop in different directions or really tweak any external parameter that we have in the simulation. And in the following, I'll only be looking at implicit representations of the surface gamma on the right-hand side. So we have a function here that maps from space-time 4D plus m dimensions for this parameter to some scalar value in order to define that implicit surface. So the surface on the right is now the level set, maybe the 0 level set of that function. And this is actually this whole space of behavior that we want to look at in the following. And yeah, this implicit representation turns out to be quite useful for the next steps. So how do we construct that? In practice, we also run a simulator that produces different 3D surfaces. We concatenate those along a time axis, shown here by these different stacks. And then what's actually important here, I don't want to go into too much detail, but essentially we're assuming that there's a similar granularity or kind of size of features in both space and time. If that's not the case, you could actually introduce some scaling, but for now we're assuming that space and time match, so we can treat them together in a 4D volume, essentially. And yeah, here in this example, the time axis would be the depth, and in the following, each of these silhouettes will typically denote a 4D volume, so I just want to have that on the slides because it's difficult to show on a 2D screen, but typically we're dealing with 4D data sets in the following. For the deformations, we are now starting with one manually chosen surface, this phi 0 here on the slides, and we're deforming that with the deformation u. It's actually quite easy to write down. You can see that here at the bottom, we basically displace the lookup of that surface with the deformation vectors to get a warped version of that initial surface, and the goal is now with that warped surface to approximate some target. So that might be some other simulation that we want to go for. Here in this example, the phi 1 in red on the right-hand side. Now, to compute how well we've done with this deformation, we can compute an error. In the easiest case, really just the L2 error over the whole domain between these implicit surfaces. What I want to point out here is that it's actually not a good idea to directly interpolate the sign distance functions. So you could actually go ahead and interpolate the phi 0 and phi 1 directly with some blending weight, but that typically actually very quickly deletes a lot of the small details. That's why the U, the deformation, is actually pretty important here to keep the data sets detailed. Now, the big question is, of course, how do we get the U? And the problem here essentially means that we have to match up different parts of the surface, as shown here by these arrows. And the surfaces from these smoke and liquid simulations can actually be very complex. They change topology and change a lot over time, typically. So this is a non-trivial problem. If you're familiar with the simulation methods, a pretty straightforward idea might be to actually use the particles that we have in FLIP and SPH, simply assign some ID, and then say, yeah, that gives me perfect correspondences, why not? That turns out to be a bad idea in practice because, yeah, if we have any interesting behavior, these simulations typically swirl the particles so much that the correspondences become pretty useless in practice. So what I want to propose here is to instead look at this in terms of an optical flow problem, which is actually well studied in computer vision. There it's commonly used for computing the how an image of a video sequence, for example, moved, and it essentially computes exactly what I just described. It takes an input, computes a deformation to get as close as possible to the target. The only kind of misleading denomination here is this optical part, which in this case there's nothing optical about it. We're using sign distance functions in practice for the data sets. Those actually turn out to have some nice properties when setting up the linear systems for the optical flow solve. That turned out to be important, but it's still the underlying algorithm is the same one, and we can actually use the established tools here from the computer vision field to hierarchically linearize the solve and compute a solution that also actually displaces over long distances in the data sets. That already gives us a basic method to perform these interpolations, actually. So if we look at this here, we have two surfaces, A and B, in red and green, both of them 4D data sets. Then we can compute a registration between the two, essentially, with this optical flow solve. And as you can see here, this is now actually, you can consider this as a 5D solve because here we have 40 data sets and some additional external dimension that we compute the correspondences across. This is actually fairly expensive in practice because the data sets can be huge, but we can do this in a pre-computation step. In practice, it also doesn't take more than a few minutes, 10 or so in practice for the data sets I've looked at. And then you can store this. And at runtime, you simply have to load this deformation, apply it, which is quite efficient. And then to produce the animation, we just cut out the time slices of the 40 data set, and that gives us the time sequence that we can display on screen somehow. So the right-hand part is typically then quite fast. And to get the in-betweens, we can simply weight the deformation between 0 and 1 to get in-between versions, for example. Let me show an example in 1D how that looks like. So here is a smoke simulation, and you can see on the right-hand side one setup where this smoke source is quite close to the obstacle. You can see this with a dashed line. And on the right-hand side, it's further away from it. And in the middle is actually now an interpolated version that deforms the data sets, in this case, from both directions into the middle. So we have a two-way deformation that's being used here. And in motion, it then looks like this. So you can see the right and left actually have quite different motions due to the interactions with the obstacle and the swirls forming here in the simulation. And the middle version now combines that behavior towards an intermediate version. Yeah, the actual surface that's used here is also an isosurface. It's really a clear surface that's defined in this case by a threshold for the smoke volume. And here you can see that. This is the actual surface for the input and the target. And here in the middle, you now see the deformed version of the input, fully deformed to match the target. As you can see, these surfaces actually also don't conserve volume, and they can actually change quite a bit over time. But the optical flow solve typically gives, due to a variation of formulation, actually a typically nice and smooth solution here. It's also good to point out again that this is space and time deformation. So here, if we freeze the time and just basically between 0 and 1 show the deformation, it looks like this. And the important thing to notice here, this is now not done in screen space. This is not a screen space warp or so, but this really moves around parts of the surface in both space and time. Yeah, I'm not the first one to look at this. So we actually had a paper with Karthik Ravindran, Chris, and Greg Turk on a similar problem with meshes. I think one of the advantages here of this implicit grid-based formulation is that it's quite robust with respect to small features. Also related in a way is a work by Matt Stanton et al. That pre-computes liquid behavior, but they actually work on pre-computed video sequences and then work with those. And I think in a way also the model reduction works are relevant, but those typically only focus on smoke simulations. And this approach actually does deal with both. It really only looks at the surface, so it can look at smoke and liquid simulations. It doesn't matter too much in practice. I want to come back to the advection part in a bit more detail, so this deformation, because it's important to note here that this is directly a nonlinear operation. So it looks quite harmless on screen. You simply add this deformation to it, but that actually makes the whole approach quite a bit more complicated right from the start. I hope that some people are directly wondering now, right, this is just moving around something. That's a step that's actually done a lot in fluid simulations. Central part there are these semi-Lagrange solves with which you can actually move around quantities on the grid. So we're kind of computing that all the time for the material derivative in the Navier-Stokes equations, especially when we don't have any change. That's really a standard thing to compute. And in this case, if we have the velocity and we know the interpolation method and the time step, then we can actually fully linearize the step. So we can bake the whole update into some matrix that's here written with this A. We multiply with the matrix, and that gives us a solution. So that is definitely possible. But the important point here is that only works if we know all these three things. If we have the time step, if we know the flow field, and if we fixed on a certain interpolation scheme. And in this case, actually, we typically do want to vary at least the time step in terms of the weight here for the interpolations. And also, we want to compute the deformation, the U itself. So in this case, we really have to deal with these nonlinearities in the deformations. And then to make things worse, I don't have time to go into too much detail here, but if we want to deal with higher dimensional parameter spaces, we actually have multiple of these deformations that we have to combine and to work with. And I just want to refer you to the paper here. There's an alignment step, how to combine multiple of these. But to give you a high level, the intuition behind it, the problem with working with multiple of these deformations is typically that these deformation fields work on certain, you can imagine, source and target regions. And here at the bottom, I have two examples where you have some shape, like the star that's actually being first moved to the left and to the top here in these examples. And essentially, in order to combine the deformations, you have to kind of warp and align them such that they work on the same part of the shape, such that they actually work together and they don't tear the shape apart or so. Yeah, but for details, I'll just refer you to the paper if you're interested. And this is an example that I've also shown in the fast forward. Right, you can blend smoke and liquid. It doesn't matter too much. The method really just deals with the surfaces of the inputs. Yeah, I also want to give a bit of an outlook about next steps here. This work was submitted or started a while ago. What I think is an interesting direction here is actually combining this with convolutional neural networks. And if we look at this parameter space, here shown with this square on the left-hand side, these optical flow deformations actually kind of give us lines and take us along, say, edges of the simplices of this parameter space. But it's actually interesting to look at the whole complex behavior in the inner region here. And right, that actually lends itself to data-driven methods, so we can sample the space. And here, for the parameter space, it's really just values for the parameters, two scalars in this case. And we can produce simulations for all of these values to get, in a way, the ground truth solutions. And the optical flow deformations actually give us some approximation of the space, but they kind of ignore the whole inner region. And for that, we can now use a neural network to, given an input for these parameters, produce with some deconvolutions directly a kind of refinement deformation field, and better approximate the middle here of this of the parameter space that was chosen. And right, this I quickly want to demo. Because once that is pre-computed, it actually does run quite fast in practice. I hope you'll be able to see that in a moment. All right, so this is now an app where a pre-trained network is running, and this has now some of these deformations for the drop setup that I've shown earlier, and now I can actually let the drop fall in with different sizes and different positions in this basin of water. I hope you can see this is now supposed to produce a larger drop, and now it's a smaller drop. So each of these would take around 10 minutes on a regular workstation, and here it's actually with the network and the rendering running in real time on a phone. So all these pre-computations actually give me a nice speed up overall. So I think this direction is one where this method actually shows its potential. Hello. Yeah, and with that I want to come to the conclusions. So I've shown a method to pre-compute behavior of fluid spaces. The key ingredient here are these implicit representations with a robust correspondence calculation. And I think especially the real-time applications are actually an interesting direction for this approach. As an outlook, there's definitely a lot of interesting work to do here. One obvious one is the method so far really only sees 4D surfaces. It doesn't know anything about the physics. It would be interesting to bring that in. Also, right now, the one I've shown on the cell phone here actually uses this combination of optical flow deformations and CNNs, and it would, of course, be interesting to purely use a generative model to only work with a neural network. And I think also other phenomena would actually be interesting and might be interesting applications here. So with that, thank you for your attention. I'd be happy to answer questions.
Thank you for the talk. We have plenty of time for questions, so please come up to the microphones if you have anything you'd like to ask.
Hi. Niels, thank you very much for the nice presentation. Andreas, that's me. Just I would like to know, did you check the physical correctness of the interpolated solution? I mean, just to see how far you are off from a real physical phenomena that you try to interpolate.
So the key quantity is really in here the distance of the surfaces. So that's something that that is being minimized by the optical flow solve, and that you can compute. However, it's not that intuitive. So we do see a good approximation with respect to basically the fineness of the deformations. So the finer you make them, the more closely you get to the inputs. But it's difficult to interpret that in terms of physical correctness. There's definitely right now, for example, no volume conservation. And while you ask, right, I didn't have time to show that, but in the paper there's actually a series of examples that show when it goes wrong. And here is one of the examples. So if the distance between the input grows too much, here in this case, I think it's actually the middle one is almost 25% of the domain, and the right one is more than that. 25% turned out to be the practical threshold in terms of distance for our implementation. Then parts of the surface actually can disappear and are not preserved. And right now, it's also not guaranteed that from over time we conserve mass or right the mass we currently should have in the system. So this is a direction where the additional physical constraints, I would hope, improve things.
Hi. I was wondering if you thought about using an interpolation strategy to generate in-between frames for a given simulation in order to slow it down.
That's an interesting direction. We haven't tried that. But I imagine you could actually, well, then you probably wouldn't have a 4D problem anymore. You'd have 3D data sets that you could match and then interpolate between. That should work. It should also be faster to solve for. But I mean, here the deformations are nonlinear. We typically use linear weights. So right now you actually wouldn't get any curved trajectories or so out of the deformations. That could be something you'd probably be interested in for extreme slow motion scenes.
Okay, thanks.
Yeah, thanks again for the talk. The speakers will be up at the front at the end of the session if you want to ask more questions. All right, so the third talk in this session is going to be data-driven synthesis of smoke flows with CNN-based feature descriptors. And the authors are Rachel Chu and Niels Turai. And Rachel will be giving the talk, or Mengyu Chu will be giving the talk.
Hello, everyone, and thank you for the introduction. So this is our topic. The goal here is to generate high-resolution smoke. With higher resolution, people would like to see more details, and at the same time, less numerical viscosity. However, those calculations are usually expensive. There are several related works investigating in the same direction, such as up-resolution techniques and image synthesis methods. Instead of using numerical procedures or image textures, we prefer to use real fluid data in a data-driven manner. So far, only few work use machine learning techniques in fluid simulation. This work shows that machine learning techniques can speed up fluid solvers. Instead of working on particular fluid solver, we want to learn general fluid descriptors. Now I will explain our algorithm. So first I will show the overview. Here we have a descriptor learning part where the convolutional neural network is used to encode the similarity between the fluid regions. At the same time, we have a deformation limiting part that deals with the flow motion. With the help of these two, we can create a reusable fluid repository. And at last, a synthesis step is necessary to generate the final detailed results. So let's start from the descriptor learning part. In this part, the input is a pair of fluid local region, and the output is the similarity between them. Let's say that 1 is similar and -1 is dissimilar. We can imagine that if you only offer the network data like those which are similar, then the network will only say that all data pairs are similar. So we should also offer data that are not similar and mark it as negative. So the next question would be how to generate those labeled input data pairs. Here we have an example. As you can see, we use a pair of simulations, one coarse and one high resolution. And then they have the same initial setup, but are then developed within their own resolution. So they will have different amount of numerical viscosity. To avoid the data become too different, we will resynchronize the low resolution version with a downsampled version of the high resolution one. And this resynchronization is done every fixed steps. In those simulations, patches extracted from corresponding local regions should be considered as related, such as this green pair. And due to our resynchronization, we can get a variety of positive data pairs as listed here. They contain different velocity, different density, and also the numerical viscosity difference between the coarse and the detailed one also varies from pair to pair. If we randomly choose patches from different local regions, then we will get non-related, non-similar data pairs. In this way, all the data pairs are automatically labeled, so there is no tedious human labeling work anymore. So based on those data, we use the convolutional neural network to encode the similarity. For the structure, inspired by some image similarity papers, we also adopt the semi-structure, which means we have two branches, and each one take one of the inputs, and inside the two branches, the structure are exactly the same, and their weight is also shared. The last layer is a flattened one, which can form the descriptor of the input. And then, if we take the L2 distance between the two descriptors, we then get the dissimilarity. As a descriptor learning approach, this semi-structure offers us many advantages. It can force the network to learn descriptors that is invariant for different resolution, and also, for our case, it deals with the different amount of numerical viscosity. Since the numerical viscosity contains the errors from all fluid simulation calculations, there is no closed form to estimate it. But neural networks can come across this problem and draw connections between data pairs just by learning through large data. On the semi-structure, a straightforward idea would be to train it according to the L2 distance directly, which means we minimize between the distance between positive ones and maximize the distance between negative ones. As shown here, if we have a white coarse sample and we have a green positive, pink negative, or in high resolution, then in the descriptor space, the network will try to drag the green positive as close as possible while push the pink negative to the far opposite. However, sometimes it's not a good idea. For example, this white sample may have a yellow negative. It is marked as negative, but still is visually similar to the green positive. And then, when the network tries to push this yellow sample to the far opposite, the green positive one will also be dragged apart, and vice versa. And this is very likely to make the training diverge. To improve this, we can use the hinge loss, where the neural network only pushes the positive and negative samples to the positive and negative margins, which is AP and AN in the equation. And then the neural network has the freedom to arrange the samples within the margins, assigning them a proper distance. In this way, the network may learn that they can push the pink negative to the far opposite while keep the yellow negative relatively closer, and we got a more stable training. So based on the semi-structure and the hinge loss function, we can train our network with different fluid data, including density data as well as velocity data. We can also use the curl of the velocity so that it tells us more about the local movements instead of the large-scale motion. Talking about the flow motion, let's take a look at the deformation limiting advection part. So here, the flow motion is separated into a large-scale motion, which is represented by our patch advection, and a small-scale motion, which is then the local movements within the patches. So a good example of the small-scale motion, A good example of our small-scale motion would be our fluid repository. By tracking patches in high-resolution simulations, local movements are recorded. And yes, this is the example of the large-scale motion. Smiley faces represents our patches. You see that the faces are not deformed that much. That is because our advection is deformation limited. And this is achieved by solving an error minimization problem. Here, we define our error as a combination between the advection error and the deformation error. The parameter lambda is used to balance between them. This is our patch. You see that it is further subdivided into smaller tiles, and the control is done on the vertices of the tile. The advection error is simply defined as the distance between the current position V and the advected position V', which is advected from the previous frame. Similarly, we define the deformation error as the distance between the position V and the desired undeformed position V star. Inspired by some mesh deformation approaches, we also calculate our V star according to its neighboring vertices based on Laplacian coordinates. And in this way, we got a squared error form. And then the minimization problem can be solved linearly by taking the derivatives. So we compare our advection method with the naive advection method on the left, which is then advecting all the vertices independently according to the fluid velocity. So we see that the patch quickly become out of shape, while in others, the patch are more robust and they also follow the flow well. We could even increase our lambda so that the motion of the patch is going to be more rigid, like this. However, in practice, we found that the left one is better in terms of separating reusable local movements. And besides patch advection, fading in time is also necessary to keep the coherence. However, it is also a little harmful for the final detail. So instead of a normal fading in, we do a patch anticipation, where patches are advected backward and smoothly faded in. In this way, the patch can keep undeformed when they are fully visible and when they match the content the best. And the fading out part is just normal, so we will just fade out ill-suited ones when they deform too much or when they do not fit the content anymore. So here we have a comparison between the normal fading in version and the patch anticipation version. As you see that although all the other parameters are the same, the normal fading version has a lot less detail due to the patch begins to fade out before they are fully visible. Now I will make a conclusion to the patch advection part. So our patch advection is used to generate our fluid repository with space-time data. It is also applied on a new coarse simulation to synthesize a detailed simulation by matching and reusing the repository. Compared to a fixed local region, this Lagrangian form offers us some advantages. It keeps the patch more stable, and which will also make it more reusable. And it also makes our method to work with any resolution, which is typically hard for other neural network methods. So now I will move on to the last synthesis part. We first have a simulation step. In this step, we have a forward pass and a backward pass. In the forward pass, we have a patch density grade and a coarse patch weight grade. So in the regions where the weight is relatively low, we can sample new patches. And a perfect match can be found from our repository. Accordingly, we should also update our weight grade. Then for all these existed patches, we advect them forward according to the coarse velocity field. And we also do fading out for the ill-suited ones and for the deformed too much ones. The backward pass is relatively simple. We just need to do the patch anticipation to fade all the patch in. And the advantage of the simulation step is that all the calculations are done on the coarse resolution. There is no high resolution data needed, and we only need little storage. For the repository, we just need to load the descriptors instead of the data, the fluid data, and the output is just the patch ID and the positions of our patch cages and the fading weights. Afterwards, we have a rendering step. In this step, we load all our patch data and further apply them with the fading weights and also a spatial kernel as you show in the right image. It helps to remove the borders of the patch. Because patch may overlay each other, it's also necessary to do a normalization according to the patch weight grade. And at last, the detailed density field is ready. Here we do have to deal with the high-resolution data now, but the good thing is that all the frames are now independent, so we can handle all of them just in parallel. Before going to the results, I would like to show something about the descriptor evaluation. Here we show it with the recall over rank, which tells us how many related pairs are matched within a given rank. In 2D, we see that this green density descriptor works already better than the blue HOG image descriptor. The HOG descriptor is typically used for image identification problems. And if we use the curl combined descriptor, which is the yellow one, it works even better than the other two. And in 3D, we can see a similar trend. It is clear that the CNN descriptor is more discriminative. And the curl combined descriptor can also improve results visually. We have an example here. On the left, that's the coarse target input, and the rest are the synthesized detailed results. In the middle, we only use the density descriptor, and on the right, we use the curl combined descriptor to match desired patches. At first glance, people may feel that all the details are acceptable, But if you take a look of the synthesized curl field, if we only use the density descriptor, then it's a bit random. And if we use the curl descriptor, it preserves the motion better. We can then zoom in into a small part to see the difference in detail, to see the difference of the motion. So let's take a look of the left one first. When we only use the density descriptor, we see more ghosting effects because patch has their own motions. And on the right, we use the curl combined descriptor, so it looks more natural. Now I will show more results. So I will start with a standard rising plume scene, and that's the gravity acting along the x direction. You see that we have a lot more detail compared with the base input, but we still keep the same large-scale motion. Our method also works with obstacles. We just advect our patches according to the cause velocity field. There is no special handling need. And here is a colliding scene between two jets. In average, there are 486 patches applied, spanning 4 seconds per frame, and it will increase the resolution to by a factor of 6. We also compared our method with the wavelet turbulence method. By working on the density directly within the same time budget, which is 2 seconds per frame, our method can increase the resolution to a factor of 8, and the wavelet turbulence method can only increase by a factor of 3. At last, I will make a conclusion by discussing the contributions and the future directions. So our method uses the convolutional neural network to encode the fluid descriptor. We also provide a rebounced patch advection method with anticipation. And based on these two, for the first time, we show a reusable fluid repository. We also offer an efficient synthesis pipeline. And we also have some limitations. Since we work on the density, there's no guarantee for the fully divergence freeness, so it would be interesting to work on velocity synthesis in the future. There are also spatial blending needed, and we also need larger storage to save our repository. Now I will talk more about the future direction. With the Spacetime repository, more data-driven approaches should be possible. Additionally, in our work, we only partially benefit from the CNN descriptors. It would be very interesting to see whether we can explore the neural networks more, applying them in all aspects in fluid simulation. So that's all. Thank you very much for listening to my talk, and I'm glad to answer.
Thank you for the talk. We have time for questions, so please come up to the microphone if you would like to ask something. So I will start. I had a question about how well the method preserves things like invariance. You talked about divergence freeness, but what about things like energy or momentum? Have you looked at that?
No, we didn't measure the energy form, so we worked on the density synthesis directly. I think it would be very interesting. So in the future, if we work on the velocity synthesis, then we can measure the energy form. Yeah, thank you.
And what about mass?
Mass. So currently, when applying patches, we do scale the patches according to the current content. So because in our repository, our patches are normalized into 0 to 1. And when applying it, we can scale it properly so that it keeps better visual looks.
Mm-hmm. Cool.
Thank you.
Go ahead.
Thank you for your presentation. I have a question about the similarity measurement. So, yeah, basically the low and the data from low and high resolution simulation data seems quite come from quite different domain, but I wonder if you have tried to use other similarity metric like structure similarity or multi-scale similarity for measurement.
Do you mean use other descriptors to do the matching?
I mean, not based on the convolution neural network, just to try to measure the similarity on the other metric like the structure similarity, SSIM, something like that.
Yeah, we do use the 2D. In 2D, we compared with the image descriptors, which is the SIFT descriptor and HOG descriptors that can match similar parts well for images. And we found that the CNN descriptors works better than them. They are more discriminative. And for other structures, I think it's not very easy to just compare the local regions directly. So I think the convolutional neural network works better.
Yeah, okay, thank you.
You're welcome.
I'll ask one. Oh, hello. I'll ask one more question.
Yeah.
How important is the simulation step? So what's stopping me from taking an existing simulation and just reading it and trying to up-res it? How important is it that we actually re-simulate from scratch instead of just taking existing data and changing and running it through your algorithm?
I think talking about the time step, our method is actually has more advantages because we save the patches in our repository and then we match the patch and use it so that it doesn't matter that much if the time steps. So for other up-resolution techniques, you probably have to advect the density for multiple steps in order to match the final resolution. But for our method, we just need to apply those patches. And yes, for the repository patches, it is good if we contain patches that contains detailed motions. And then by applying them, we think we overcome from the problem that the time step should vary in different resolution.
So what if I wanted to take a low-res simulation, use your method to increase the resolution, and use the output of that, send it into your method, increase the resolution, and keep doing this until some limit is reached?
I think it would be very interesting. Although, so you will see some large-scale movements and some small-scale movements looks similar in some way. So I think it might give you some interesting view.
Okay. Thank you very much for the talk.
Thank you.
That's it.